long as we can assume that the forces act on the center of mass. And the center of mass is the mean position of the mass in an object. So we talked a little bit about this last time, right? That said, when there's the center of mass, the center of gravity, which is the point where gravity appears to act. So for many objects, these 2 points are exactly the same. But they're different only in the same, they're only the same when the gravitational field is uniform across an object. So around Earth, for instance, the center of mass will be equal to the center of gravity. So if we're looking for the center of gravity of this wrench, what we're going to do is take the average of the mass times its position. And we say that the center of mass will be up around the head of this wrench. And actually, if you toss this wrench, it'll follow the same trajectory as we saw with projectile motion. The only difference is that it'll spin around its center of mass, and it's actually this point, the center of mass, that actually follows the projectile motion. So for example, if we toss this wrench into the air, what'll happen is it'll keep spinning around, but its center of mass will follow exactly the trajectory we looked at when we were tossing baseballs and things like that. Here's a rather dramatic example, right? This is a dirt bike rider, and they're doing a flip if they come off of a hill, right? And you could, it's might be a little hard to see, but here's the motorcycle rider, and their center of mass follows this trajectory that I drew in. But if you look, they keep spinning around, and they keep spinning around their center of mass. So if we're going to talk about the center of mass, we need to figure out what the center of mass is. So if we, and this is where we were talking about it last time, we said if we consider 2 equal masses and they're separated by a rod, and let's say the rod is 1 meter long, and the mass of the rod is really insignificant compared to the 2 huge masses at the end. And if you tried to balance it on your finger, where would you place your finger? So you probably said, well, I'd put my finger like at the halfway mark. And the reason is because the gravitational force of this one is pulling down, and the gravitational force of this one is pulling down. And since they're both equal, if I put my finger in the center of it, it'll balance it out. Okay. So you probably think that the point of balance between these 2 masses in the rod is halfway between the 2 masses. So if this is a 1 meter long rod, then I'd stick my finger at half a meter and I could balance this. If on the other hand, right, and by the way, you can do this with your pen. So if you have a pen sitting there, if you try to balance it on your finger, right, about the halfway mark is where it would balance, right? If instead one of the masses was much larger than the other one, so in this case, it's twice as large, and I wanted to balance this so it wouldn't spin, for instance, right? I'd probably put my finger closer to the 10 kilogram part, right? And what we actually do is take an average of the position. So we take the mass times its position plus the mass times its position for how many masses there are. In this case, there's just 2. And divide it by the sum of the masses. So this is like the average of where the masses would be related. So for instance, if you were taking tests, right, then X1 would be the number of, would be, say, your test score 80. And M1 would be the number of times you got an 80. And M2 would be the number of times, say, you got a 70, right? And then divide by the sum of the mass of all the test scores. So really, this is like the average position of the masses. So if I look at this one, where I have 5 kilograms and 5 kilograms separated by 1 meter, right? I'll call this point x equals 0, and this point over here, x equals 1. So I take 5 kilograms times 0 plus 5 kilograms times 1, and that equals 5, right? Divided by the sum of the masses, which is 5 plus 5. So I get 5 over 10, or half a meter. So the center of mass here is at half a meter. The one where we had 5 kilograms and 10 kilograms, once again, I'll call this point 0. And then this point where the 10 kilogram mass is will become x equals 1 meter. So I get 5 kilograms times 0 plus 10 kilograms times 1 divided by the sum of the masses. This is 10 meters divided by 15, or 0.67 meters. So if this is 0, I'm going to put my finger about 2/3 of the way down. And that balances this, right? So it doesn't, so I could balance it on my finger. Life doesn't just exist in one dimension, so we need to consider all 3 dimensions. So we have X, Y, and Z, right? And sometimes we don't have to worry about Z very often, okay? And we only think about 2 dimensions. So let's consider this here. Here we have a rod that's 1.5 meters long. And we're going to stick M1, which is 1.6 kilograms, and M2, which is 1.8 kilograms. And M1 is going to be at 0, and M2 we're going to put at 1.2 meters. Okay, and this is free to move around, right? But for right now, it's at x equals 1.2 meters. So I get 1.6 times 0 plus 1.8 times 1.2 divided by the sum of the masses. So if you think about it, right, since this mass is heavier, if I want to balance this, I'm going to stick my finger closer to M2. However, they're not very much different, right? This is 1.6 and 1.8. And this is at x equals 1.2 meters. So exactly halfway is 0.6. So I'm going to move my finger just a little bit over and balance this thing. So here's an example in 2 dimensions. Here we call this point 0, 0, where M1 is. And if we, M3 is at 0, x equals 0, y equals 1.1 meters. And M2 is at y equals 0, and x equals 1.2 meters. So now to find the x position of the center of mass, we get 1.6 times 0 and 1.8 times 1.2, And also 2.3 m3 is also at x equals 0. And then divide by the sum of the masses. So our x position for the center of mass is at about 0.38. So it's about a third of the way down this rod. For the y center of mass, we'll start out with m1. So that's 1.6, but its y position is 0. So we'll multiply it by 0. 1.8, but once again, its y position is 0. And finally, 2.3 times 1.1. And then divide by the center of mass. What we find out is that the center of mass is here. Okay, so if you can think about, if you could do this in your head, if I were to grab M2 and then toss this thing to my friend that's a couple feet away or a couple meters away, what would happen is this thing would rotate as it's flying through the air, and its center of mass, this position X, would follow the projectile trajectory, just like we talked about it in chapter 2. Okay, so the important thing to remember is that for now, what we used to just consider all things, all the forces that were acting on the center of mass, and we didn't really explain it. And now we're saying that that's in fact true, that things are going to act on the center of mass. All right, so if you think about it this way, right? Here we have the total mass of the system times the acceleration of the center of mass, right? And it's going to equal the first mass times the acceleration plus the second mass times its acceleration plus the third mass times the acceleration up to however many masses there are. And Newton said that the mass times the acceleration is equal to the sum of the forces, right? Okay. And what we find out is that it's equal to an internal force plus an external force. However, according to Newton's third law, this internal force is equal to 0. Therefore, when we apply a net external force, it acts on the center of mass and it has some acceleration. We can treat forces acting on a mass as if they're exerted on the center of mass. And this is what we've been doing all along, but we never told you why we could do it. And this is why. Okay, so in this example, the only external force acting on the rider, if you neglect air resistance, right, which there probably isn't much of, is the force of gravity. So the force of gravity, the weight of this rider is pulling down the whole time, right? And just like when we were tossing baseballs, they follow this trajectory. And now the rider follows this trajectory even though they're spinning around, right? And you can think of the internal force as the force that's making the person spin, right? So they did something to make the bike begin to spin. And the external force, the gravitational force, is acting just on that center of mass. Okay, so why did the cyclists spin anyway, right? So what made them spin? And what we need to do is talk about something called torque. So in the linear case, If you wanted to get a car to move faster, you applied a force, and that force acted on the center of mass. If I want something to spin, I need to apply a torque. And normally, probably the easiest thing to think about when you're thinking about torque is a wrench. And I'm hoping at some point in your life, you've all tried to turn something with a wrench. Is there anybody who has never touched a wrench before in their life? Okay, just to make sure there's people out there, right? Anybody use a wrench before?
Yes.
So has anybody ever used a wrench before?
Yes.
Yes.
Well, let me ask another question. Can everybody see the slides?
Yes.
Yeah.
Or can anybody see the slides?
Yes, I can see the slides. Yes.
Okay, so sorry, not sure why that you were all muted. I just unmuted you all, but it didn't seem to work. But anyway, so here we have a wrench, right? And when you go to turn a wrench, what you usually do is apply a force, and there's this angle that the force makes with the x-axis. So here's the radius of the wrench, right? And the object is to turn the bolt. And if we turn the wrench clockwise, we consider that, I'm sorry, if we turn the wrench counterclockwise, we consider that a positive angle. And this, by the way, is the angle phi, PHI, and we usually use it just as to indicate that it's a torque. And this is just an angle. And what we're going to do is we'll apply this torque at some distance from the point of rotation. And what we'll see is that if we think about it, if we hold the force at some angle, it's only the part of the force that's perpendicular to the radius that actually gets the bolt to turn. So what we find is that the torque, and for torque we use a lowercase tau, that's TAU, and the magnitude of it is equal to the magnitude of the radius times the perpendicular component of the force, which in this case will be F times the sine of theta. Or we can say it's just equal to the perpendicular component of the force. So the magnitude of the torque depends on the magnitude of the force. It also depends on the direction of the force. And it also depends on the radius of the length that we're going to apply the force. So we say that this is a vector, that torque is a vector, and it's equal to R cross F. So if you remember when we talked about work, we used something called the scalar product. We said it was equal to force times the scalar product of the distance. For torque, we use the cross product. It's also known as the vector product. So in this case, if I increase the angle, my torque becomes larger. And the larger the torque, the largest the torque can be is if the angle is 90 degrees. Okay, so here's the idea. The magnitude of the cross product is equal to R times F times the sine of the angle between them. The direction of the torque follows the right-hand rule. So in this case, it's actually perpendicular to both R and F. So if you think about it, if you turn this bolt here, you have one of two objectives. You're either trying to drive the bolt into the block of wood or whatever, or you're trying to pull the bolt out. And that's the way the torque is. So for instance, if I think about this radius R and the force, there's only two positions that are perpendicular to both of these. And that would be out of the page and into the page. So the direction of the torque follows the right-hand rule. So this is a little crazy, but what you have to do is take your hand and you're going to hold it like an L. So you take your hand and you hold it like this. And then you put your hand in the direction of R. So in this case, R is going to be in the positive X direction. And then you make your fingers so that they are curl towards the force. So in this case, the direction of the torque is into the page. In this case, you put your hand the other way and curl your fingers, and your thumb points in the direction of the torque. So if it's set up like this, the torque is out of the page. And if it's set up like this, the torque is into the page. In this case, we're loosening the bolt. And in this case, we're tightening the bolt. So the important thing to remember about the torque is that it's the cross product of R and F. And the magnitude is equal to R times F times the sine of phi, which is another way of saying it's R times the perpendicular component of F. And the direction follows the right-hand rule, and it has to be perpendicular to both R and F. Okay, so here's an example. Here we have 100 Newton force, and I'm pulling this way. And normally, if you use a wrench, what you're going to do is pull in this direction. The reason is because you don't want the wrench to slip off the bolt. So you're going to use some of your force, the X component in this case, to make sure that the wrench stays on the bolt. This perpendicular component is the part that's actually going to turn the wrench. So what we end up here is, if we look at the perpendicular component, it's going to be the force times the sine of this angle. Okay, so in this case, our wrench is about 3/4 of a meter long. So it's 0.7 meters. Our force is 100 newtons, and our angle is 120 degrees. And the units for torque are Newton meters. So it comes out to be 60.62 Newton meters. By the right-hand rule, right? Once again, we're going to put our hand in the direction of R, and then put our fingers such that we can curl them towards F. So in this case, the direction is positive and it's out of the page. Okay, so in this case, we're actually loosening the bolt. There's another way to look at this. Okay, here we have the length of the wrench. All right, and if we look at the X and the Y components, we end up with 100 newtons times the cosine of 120. and 100 newtons times the sine of 120. So our force is in the x direction, negative 50, and in the y direction, plus 86. And there's nothing in the z direction. So there's no force in the z direction. Okay, so if we look at r, it just points in the positive x direction. So if we write it in IJ notation, we get 0.7 meters, 0 meters, and 0 meters. Sorry, these should be m's. Okay, so this is something called a determinant. And the idea is this. We write the determinant as I, J, and K, right? And then we write our vector R. Vector R is 0.7 meters in the x direction, 0 meters in the j direction, and 0 meters in the k direction. Next, we write our force. Minus 50 newtons in the I direction, 86.6 newtons in the j direction, and nothing in the k direction. Okay? All right, and if you've ever have considered using determinants, there's a little trick we can use if it's a 3x3 determinant. And the determinant just means that you're doing R cross F. So here's the little trick. We can rewrite the I column and the J column, so the first and second columns. And then, I know this sounds crazy, but what you do is multiply through on diagonals, and I'll draw it on the board in a second. So what we do is take these diagonals and multiply them together, and you add them. So this is I times 0 times 0, which is written here. And it's J times 0 times negative 50. And it's K times 0.7, 0.6, 86.6. Okay? So next you have to subtract in the opposite direction. So we draw diagonals this way, and we get minus negative 50 times 0 times K. And then minus 86.6 times 0 times I. And finally, 0 times minus 0 times 0.7 times J. So this first term is 0, the second term is 0, this third term is 0.7 times 86.6 times K, and then 0 times 0 times 0. We end up with plus 60.62 Newton meters times K. All right, so you might say, what's the use in doing this? And the good thing is that we don't have to use the right-hand rule to do it. So this tells us that the torque points in the positive K direction. Okay, so determinants are really interesting things, right? And if you do more math, you'll learn more about them. For now, it's just a way to do the cross product for this. By the way, this little trick of using these diagonals, in case you do more math, only works for a 3x3, but that's okay because we live in a three-dimensional world. So for physics, it's just fine. So as I said, I'm back in Philadelphia, so you might hear lots of sirens at certain points. So here's another example. Here, what we're going to do is I want to get a bowling ball to roll, okay, or a disc to roll. And what I'm going to do is apply a force of 10 newtons, and it's going to be at an angle of 60 degrees. And the radius of this disc is 0.1 meters, so 10 centimeters. So if I look at r in this case, it'll be 0.1 times the cosine of 60 and 0.1 times the sine of 60. So we end up with 0.05 meters I and 0.9 meters J. And it doesn't point at all in the K direction. Once again, sorry, these are supposed to be meters. And if I look at F, it has no I component and no Z component, and it's pointing straight in the Y direction. So now I draw up my determinant, I, J, K. Then I write R, which is 0.05, 0.09, and 0. And then write the force, 0, 10, 0. Then I rewrite the first two columns. Okay, so this is probably the toughest math concept you have to do this semester. And what we do is multiply down this diagonal. So this is I times 0.09 times 0 is 0. And J times 0 times 0, 0. And then we get K times 0.05 times 10 is 0.5. So we have 0.5 K. Then we subtract in the other direction. Minus 0 times 0.09 is 0. Minus 10 times 0 is 0. Minus 0 times 0.05 is 0. So we end up with our torque is equal to 0.5 Newton meters in the K direction. Or notice that the angle between the radius and F is 30 degrees because this is 60. Then we could do it R times F times the sine of the angle. So that's 0.1 times 10 times the sine of 30. We get the same answer. The only difference is we need to figure out what the direction of the torque is, and we have to use the right-hand rule for this second one. Okay, so if you remember, back in I forget if it was test 1 or test 2, I think, exam 2, we talked about static equilibrium. So for example, what we wanted to do was we were going to hang this sign, and it's a 100-kilogram sign. And what's going to happen is the weight is going to pull straight down. And then we have this tension T1 and this tension T2. And let's say these angles look like this, right? So we wanted the sign to hang in this direction. All right, so if we look at the x components, and we take positive y, x to be in this direction, right? Towards this side of the page is positive x. Then what we end up with is minus ft1 times the cosine of 60 and plus ft2 times the cosine of 40 equals the mass times the acceleration in the x direction, but we don't want the sign to move in the x direction. Then we look at the sum of the forces in the y direction. So that's ft1 times the cosine of 60. It's pointing up, so it's positive. ft2 times the sine of 40, it's pointing up, so it's positive. And the weight, which is pulling down, and it's equal to minus mg. So we can solve the x component for ft2, and then we plug it into the y component. So we plug in ft1 cosine of 60 over cosine of 40 in for ft2. And then we can solve for ft1. So we get 100 kilograms times 9.8, the sine of 60 plus the cosine of 60 cosine of 40 over the sine of 40. And if you plug that in your calculator, you get about 7.62.3 newtons. Okay, and then you can plug this back into this equation and find out what ft2 is. And we end up with about 500 newtons. Okay, so this was static equilibrium. We didn't want the sign to accelerate in the x direction, and we don't want the sign to accelerate in the y direction. We want it to just sit here. Okay. But there's another problem, right? If we consider this, and what this is called is a block and tackle, but that's not important. What it is that you're trying to hold up this 100 kilogram weight, or 100 kilogram mass. And it's being held on the edge of this beam. And you have this rope here. Well, what we've found is that we could put this in static equilibrium and the thing won't accelerate this way and it won't accelerate this way. However, it could twist. So what will happen is here's this beam and we put this big mass on it and the beam starts to twist. So now not only do we have to worry about the sum of the forces in the x and the y direction, and we need them to be 0, we also need the torques to be 0. So if I want this thing to hang here without falling apart, without this beam bending and twisting, right, or rotating, we have to not only sum up the forces in the x and y direction, we also have to sum up the torques. So here's the idea. At the end of this beam are two forces. There's one that's acting up, and there's one acting in the horizontal direction. So this might be bolted to the wall, but there's some force here, and I can look at it as a horizontal and a vertical force. The forces here at the wall are very complicated, but I don't care. I'm just going to sum them all up and make the horizontal and the vertical component. We also have the weight of this beam pulling down. And we have the weight of this hanging mass pulling down. So if we look at the weight of the beam, it's 40 kilograms times 9.8. It's about 392 newtons. And if we look at this weight that's hanging off the beam, by the way, this 40 kilogram thing is the beam, right? Okay, we get 100 kilograms times 9.8, or 980 newtons. And now we have to have a cable here so the thing doesn't just fall apart. And the object might be to find out how thick we have to make this cable. Right? So we're going to set this thing up. We know we want to build this little block and tackle, as we called it, right? And we need to know how big a cable to buy, how thick. All right. So now we have to consider not only the forces, which have to be in equilibrium, we also have to consider the torques. So for the first condition of equilibrium, we need the sum of the forces to be 0. That means that the sum of the forces in the x direction have to be 0, and the sum of the forces in the y direction have to be 0. And we won't ever care about the z direction, but the sum of the forces in the z direction also have to be 0. Okay? So don't forget, the sum of the forces always equal the mass times the acceleration. However, we don't want it to accelerate in x. We don't want it to accelerate in y or z. We also don't want it to rotate. So we don't want it to twist or turn. Okay? So we also have to sum up the torques, and they have to be equal to 0. So in our example, what we're going to do is write all the x components of the forces. So there's only 2, right? There's this horizontal force that I don't know what it is, but it's acting in the positive direction. And there's the x component of the tension in the string, or the cable. That's going to be the force of tension times the cosine of 30, and it's pointing in the negative x direction. Then we sum up the forces in the y direction. Okay, so definitely the weight of the beam points in the y direction, and this hanging mass points in the y direction, and they're both negative. So that's 980 newtons and minus 392 newtons. Also in the y direction, we have this vertical force. And finally, we have, and it's positive, we have the y component of Ft, which in this case is Ft times the sine of 30, and it's also pointing in the positive y direction. Okay, now here comes the new part and the hard part. We need to figure out the torques. Okay, so this is bolted to the wall here, right? Okay, so I think if things are going to rotate, they're going to rotate around this point at the wall. And this is what I mean. If this cable suddenly snapped, right, I think everything will start moving this way. But it's attached to the wall, so it can only rotate down towards and fall this way. Or let's say that I really increased the force of tension, right? So I pulled here. This is attached to the wall. So that means that it would move up this way. Okay. What that means is that this vertical force and this horizontal force can't make it rotate. All it can do is make it stay at the wall. Another way of thinking of it is that if I know this is the point of rotation, then the distance from the point of rotation to these forces is 0. Okay? All right. So now I have to worry about the other forces. We said the torque was R cross F, right? Or R times F times the sine of the angle between them. So here, let's look at this hanging weight first. Its R, its distance from the point of rotation is 6 meters. And the weight is 980. And it would turn it in the negative direction. Okay, so it would turn it in the negative direction. So we end up with minus 5,880 Newton meters. The beam also has some weight. And the weight of the beam is 40 kilograms times 9.8. It's 392 newtons. And the angle between the weight and R is 90 degrees. So all of the weight is trying to get it to turn. So we end up with minus 392 times 3 is negative 1,146 Newton meters. Both the weight of this beam, so maybe this is a big metal beam, and the weight of this hanging mass are both trying to turn it the same way. Finally, we have the force of tension, and the force of tension times 30 degrees is its y component, and it acts at 6 meters, right? Now, just like we did with the static equilibrium problems, we're going to add up all these, they have to equal 0. Add up all these, they have to equal 0. Add up the torques, they also have to equal 0. So first, let's do the torques. We get f of t times the sine of 30 times 6 minus 5,880 Newton meters minus 1,146 Newton meters. And we solve for the force of tension, and we end up with about 2,000 newtons. Okay? So now I can figure out how thick to make the cable, because I know what the tension in the cable will be. All right, so the first thing I did was sum up all the torques. Just read straight down this column. I want it to equal 0 because I don't want it to turn. And I sum up the forces I can solve for the force of tension. While we're at it, let's figure out what these two forces are, FH and FV. So now what I'm going to do, I'll sum up the forces in the x direction. I get minus FT cosine of 30 plus FH is equal to 0. And I solve for FH. And hold on 1 second. Hey, Rose, your phone's ringing. Sorry about that. We got back to Philadelphia and the air conditioner doesn't work, so I had to go answer the phone. Sorry about that. Okay, so then we sum up the forces in the x, y direction, and we end up with Ft sine of 30 plus Fv minus 980 minus 392. Okay, and we can plug in for the values, and we end up with the vertical force is 201 newtons. Okay, so whenever we have something that has the possibility of turning, we also have to add up the torques. Okay, so normally when we look at a torque problem, okay, we look at something called levers, all right? And here shows two kids on a teeter-totter, a seesaw, whatever you want to call it, okay? And what it consists of is this triangle here, and the point that you're trying to get it to rotate around is called the fulcrum, right? And what we'll have is it's applying a force in this direction, and it's a contact force, okay? And here we have two kids, and one of them's a little bit older than the other, so one of them has a higher mass. So M2 is greater than M1. And in this case, if I want this thing to balance, then M2 would have to sit closer to the fulcrum. Because remember that center of mass thing? Okay? So F2, so the bigger mass would have to be closer to the fulcrum, right? And by the way, this is the last slide. Sorry, it's 10:03, I just realized. Okay? So this is what's going to happen. We look at the forces. In this case, we don't have to worry about any forces in the x direction. What we'll end up with is this force of the fulcrum pointing up, and then minus M1g minus M2g. If we didn't consider the torques, what could happen is these could sum up to be 0, and yet the teeter-totter still twist, or the seesaw still twist. Is that okay? So we also need to sum up the torques. In this case, we get the weight times R1, and it's trying to turn it in one direction, the positive direction. And then we get the weight, M2G times R2, and that's trying to turn it in the negative direction. Okay? And what we're trying to do is get this thing to balance perfectly so that it doesn't move up or down and it doesn't twist. So then we sum up the forces in the y direction. And not surprisingly, the fulcrum applies a force that's equal to the sum of the two weights of the children. And if we look for the torques, we want them to sum up to be 0. So we'll read straight down the torque column, and we can solve for the ratio of R1 over R2. Okay, so this is actually a problem taken straight out of the book. All right, so we know that, for instance, if the mass of M2 is 10 times the mass of R1, then the distance for R1 has to be 10 times the distance to R2. That's what they're trying to show you here. All right, so we'll talk more about this next time, about torques. And